In this video, we'll look at electric potential difference and electric potential. Now, as our starting point, I'm going to assume that you are familiar with the basic definition of electric potential difference, namely that delta V is equal to minus integral E dot dr. From there, we're going to begin by deriving V equals KQ over R for a point charge, and then we'll talk about integrating over charge distributions. So let's begin by deriving the point charge formulation. And we're going to consider a point charge, capital Q. And we're going to find the potential difference between a point at distance RA to a point at a distance RB. So to begin with, we know that the electric field of a point charge is KQ over R squared, R hat. And so what we can say that delta V is equal to minus integral KQ over R squared dr, evaluated from RA to RB. So more precisely, this would give us the difference, V of RB minus V of RA. Let's go ahead and evaluate this. So what we find is that the integral KQ over R squared, that's going to be equal to negative KQ over R. Remember, we have an overall negative sign out front as well. Evaluated from RA to RB. And so what does that give us? I'll cancel the two negatives. We end up with KQ over RB minus KQ over RA as our result. Now, to begin with, let's just do a quick intuition check about whether we have the correct sign. So since RA is less than RB, the overall sign of this is negative, since KQ over RA is larger. Does that make sense? Yes, moving along the direction of electric field gives us a decrease in electric potential. So now let's consider the following case, which is suppose I want to set a fixed reference point. So what we're going to argue is we're going to say V at infinity is 0. So we're setting a reference point, which we can now use. If we go back to our formulation, this would correspond to wanting to take the limit as RA goes to infinity of KQ over RB minus KQ over RA. So we end up with KQ over RA goes to 0, and we simply end up with the formulation KQ over RB, which I'm going to leave now as KQ over R. So this is our point charge formulation. With that established, let's consider when we use which formulation. When does it make sense to use delta V equals minus integral E dot dr to compute electric potential difference? And when does it make sense to use V equals KQ over R? The essential idea is as follows. Delta V equals minus integral E dot dr is going to be extremely useful when the electric field is known, and especially when it has nice symmetries. So if E is known, or Gauss's law applies, we're generally going to use formulation 1. Formulation 2, KQ over R, obviously we'll use for point charges when we want to know the potential difference in the vicinity of a point charge. But if we have charge distributions for which we would find the field via direct integration, so for example, a charge distribution that is a short rod so that we cannot apply Gauss's law, or a ring of charge. Those are examples in which E is fairly complicated. We would need to find E via direct integration. This is where instead we will want to use V equals K dq over R and go ahead and integrate. So in the next two videos, I'll go through examples for each of the two cases, but we'll wrap up here with that theoretical overview.